Here we go. Press S. Oh. So, how would I be able to mirror something? Shift A and Q. Oh. Used topology based memory. Right on. Okay. Mirror. Okay. That's what I needed. Oh, that just does this. It doesn't do a separate cube. Okay. selection. Oh, no, that's the grave key. What I need to do is I need to Shift D and then wonderful. So now I got two objects. Subdivide twice. Same with this one. And then select all. Control Shift S. Oh, no, no, no. That's wrong. Shift S. No. Shift Alt S. Yes. Why is this acting weird? Shift Alt S. Subdivide, subdivide, delta, basis, P, tab, Shift Alt S. That why does that look weird? that is not the right location. +2, -2, 0. Why does that... Wonderful. Now that looks correct. Why? I hate how that circularizes. Wonderful. Okay, so now... Subdivide, unsubdivide. C. No. V. Z. I may need to start off with a different cube. Complete. Okay. Shift A. Mesh. Cube. Two. Five. Size 1. Yes. Then what I need to do is subdivide, um, S. Okay. Perfect. So that's circularized properly. Wonderful. Now I can shift D, 0, 0. Wonderful. So now both of these have a circularized shape key. Now I need a new cube. There we go. Point 5. G, C, negative 0.5, negative. There we go. So now I select all, subdivide, subdivide, and then I need to add shape key, Shift Alt S, circularize, unsubdivide, unsubdivide, G, C, I, again, Subdivide. Okay. Hmm. Transform. How do I transform things? Object. Properties. Okay, there we go. Dimensions. Still needs to be 1 by 1, but the Z needs to be... Let's try 6? No. 6 is too much. 3. 3 is still too much. 2.5? Subdivide. Control. Control R. shift. So basis shaky tab. Shift A. No, not Shift A. Control A. No. A. Just A. Shift Alt S. Turn into sphere. Perfect. Now it can just be that, and then we can scale it. Point 8, 0.9, 0.8. G, C, okay. Shift D, and then have that be -3. Yeah. Perfect. Perfect, perfect. Oh yeah, it's all come together. Okay. So E, have that be -0.5. There we go. Hmm. Shift A, mesh. Cube. This. X. Shift D. It's negative 1.5. Wonderful. The hands and feet, I don't think I'm going to give a shape key. Wait, 3. Wait, 3. 3. Wait, 3. Wait, 3. Three. 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 Would you look at that? Would you look at that? Wonderful. G. Let's see. R. There's a reason why they T-pose, right? There's a reason. What's this? 9. G. Well, there. Negative. Negative. 3.5. No. Negative 3.85. Negative 3.85. 6.35. Negative 6.35. 7.8. Negative 7.8. That's gonna be 0. Why is that negative 0? What the hell is a negative 0? Okay. Now that I have this, I have to figure out rigging. Okay. Let's oh, nope, that's the thumbs down. I need the like button.
most essential parts of animation. It's your main interface with the character and the way you animate, on top of which the whole thing is built. So it's important you have a good rig, because a good rig will make your life a lot easier, while a bad one is gonna make it hell. And I'm here to teach you how to make good ones. So listen up, take notes, and subscribe. When it comes to rigging, we always think of skeletons, or armatures as Blender calls them. Although you could technically make a fully functional rig without any armatures whatsoever. You can parent multiple objects in a hierarchy and make them move just like a rig, so what's the point? Well, for one, armatures are much more organized. Two, they let you do so much more when it comes to constraints and controls and stuff like that. And three, they make exporting animations 1,000 times easier, so let's learn what they are. Armatures are chains of bones in a hierarchy with a head and a tail. The head is the pivot point and the tail is the end point of the next bone. They can be connected or disconnected, parented or unparented, or a part of its own hierarchy altogether, depending on your needs, of course. Once you have an armature, you can assign geometry to it and it will move with the armature. Technically, all you really need is the pivot points on these bones, since those are what drives the transformation, but having the tail there makes it easier to visualize. In Blender, press Shift and A to add an armature, and this thing you see in the viewport is a single bone. We can make a simple bone hierarchy by hopping into edit mode, selecting the head or the tail, and extruding it to build the tree. You can change the bone's parenting or connected attributes in the bone properties panel in the relationships dropdown. If you want to preview how the hierarchy works, you can do that in edit mode. This is where you set up the skeleton. You need to hop into pose mode by pressing Ctrl and Tab or visiting this dropdown up here. This is where you get to move, use, and animate your rig, and you can see exactly how your bone chain works based on the hierarchy you've set up. Okay, but how do you actually assign geometry to it? Well, that depends on what you're rigging. First, we need to talk about skinning. Skinning is a process of assigning the influence of each bone on the rig to individual vertices on your model. The values go from 0 to 1, where 1 is full influence, 0 is no influence, and the values in between are partial influence. It's easiest to depict as a gradient. Any vertex can be affected by as many bones as you want, as long as all the influences add up to 1. Usually that influence, or that weight, is painted by a brush. That's why this process is called weight painting. Huh? We know two approaches to skinning. On one hand, we have rigid or separate type of skinning, and on the other hand, we have bendy/deforming. I'll explain both and I'll rig my own character in the end to put everything into practice. First up, we've got rigid type of skinning, which is the simpler of the two. Rigid skinning is used when your character is made up of multiple objects and none of them deform. They just move along and rotate. You'll often see these kinds of rigs on robots. The way you do this is by hopping into pose mode on your rig, selecting the bone you want to parent to, then hop back into object mode. That bone is still technically selected, so now you can select your object, or multiple objects, then select the armature last, so the armature is the active selection, press Ctrl P to parent, and select bone. So all these objects are now parented to the selected bone. Alternatively, you can select all of your objects, then select the armature last, press Ctrl P to parent, and then pick Parent to Armature with empty groups. Technically, all these objects are now parented to the armature, but they're not assigned to any bone, so far nothing happens. Now, however, the objects receive new vertex groups in the Object Data Properties tab, and those groups have the same names as your bones. Here's another reason to keep your bones nicely renamed. I always say organization. It makes things so much easier. Now you can select all the objects, hop into edit mode, then select them with the L shortcut. Then in the vertex group, select the bone you want to parent your selection to, make sure the weight is set to 1, and click assign. You've technically weight painted this entire object to that bone by giving it a value of 1, so now it's gonna move with it. There's much more visual ways to weight paint, and we'll do that in a second. Don't worry, just wanted to show you this. Once you do this for every object, you should have a rigid rig that moves the parts around without deformations. If you want deformations though, you need to do weight painting, which I've mentioned before, which is where bendy skinning comes into play. As mentioned before, weight painting is a method of assigning weight to different vertices on your mesh to the bones on the armature to ensure proper and wanted deformation during the animation. That was a heckin' line I did. This bone will affect these vertices by this much, and that bone will affect those vertices by that much. Again, we sort of did that in the previous step. We just assigned the maximum weight to full objects. Now we're just gonna do it with a brush. Okay, assignment time. To rig this guy, first make the middle row of bones, starting at the crotch, so that's our main root bone, and rename all of them. Now make one of the sides.
Okay, Shift A, armature, and I'm gonna go to here, G, Move it up. How do I toggle X-ray? Okay.
And rename that as well. Select all the bones on the sides and press Ctrl and F2. Since F2 is a shortcut that renames things and Ctrl and F2 is a shortcut that batch renames things, it makes sense. Set this box to selected and bones. Set the type to set name and the method to suffix, meaning it will add something at the end of the word. That's what a suffix is. Put the name to .l, which will add a .l at the end of your existing name. It's important to put the dot before the L because that's how Blender recognizes namespaces, which will make the next step possible. Select the side bones and then right-click and click Symmetrize to mirror the bones. Because of the naming convention we used, the bones are flipped and the .l turns into .r automatically, so the naming is all done. Just a tip. Now that the armature is all set, we need to bind it to the model, and the simplest way to do this is to select your model, then the armature, press Ctrl-P to parent, and here choose parent to armature with automatic weights instead of empty weights this time. This basically did the weight painting automatically, which is very cool, but it's not the best, so we'll probably have to tweak this later. But for now, your model moves! Woo! This step also works with multiple objects at a time. Now to fix the weight painting, we need both the model and the armature selected, but the model has to be the active selection this time, because weight painting is an attribute stored on the model, not on the rig. So select the armature first and the model second, and then, through Control-Tab or this drop-down here, enter weight painting mode. Here you'll see a rainbow. In short, the highlighted bone is the one you're painting the weights to, and the colors represent the weight itself. Blue is 0, meaning no influence, and red is 1, meaning max influence. To switch between bones, hold down Alt and click. You have a brush where you can press F to change the size, or Shift F to change the strength. Additionally, you have the strength slider at the top, as well as a weight slider. So the weight slider is the weight you want to paint, and the strength slider is like an opacity for the brush. If you want to fix the weight painting, you're basically trying to paint more or less effect in different areas.
Wait, hold on. I think the video has been a lot quieter than the music, hasn't it?
For each bone. For example, here it's dragging too much of the behind, so I'm painting that out. It's always smart to pose the bone first and then do the weight painting on the pose, so you already see what it's going to look like when it's deformed, and it's easier to see where where all the issues are. You might run into deformation issues in places where you don't have enough subdivisions, since deformation happens on the vertices. Simply add more, adjust your weight painting, and it's all gonna be fine. To paint the weights from scratch, parent your model with empty groups, hop into weight paint mode, and in the options drop-down, turn on the auto normalize option. Since each vertex can be influenced by multiple bones at once, this option will limit the weight, so the maximum it can have across all the bones combined is always going to be 1. That means if you paint over an area which is already assigned to a different bone, the value will be taken away from that bone to accommodate for your brush stroke. Once you have this set up, select the root bone and paint the whole model. You can make use of the gradient tool by dragging it away from the mesh so it all turns red, and because of the auto normalize option, this bone is now the only bone with any effects on the mesh. Then select the next bone in the chain and paint everything from its effect up, which will take that away from the root bone. But that's fine since the root bone is still the parent of this bone, so when you move it, it's gonna look normal because it moves with it. It doesn't matter. Then simply move up the chain and paint each next bit until you have the weight painting all done. You can help yourself with masks. Select your mesh, hop into edit mode, and select the area you want to mask out. With this area selected, exit edit mode, so these vertices are still technically selected just like with the armature before. Now select the armature and mesh and hop into weight paint mode. Because this area is still selected, you can use it as a mask up here, either by showing you the faces or the vertices. It's just a display thing, they both do the same thing.
Okay.
This is the only area you can paint on. This is useful if you want to use the gradient tool to help you paint, but you don't want to mess up the rest of the model. Anyway, here are some other weight painting tricks you can use. You can assign automatic weights only to the selected bones, by first selecting them in pose mode, and then going back into object mode. Then select your character, hop into weight paint, then open the weights drop-down and click assign automatic weights from bones. This will give automatic weights to selected bones, but will leave your other bones alone. You can drop down the display option and turn on wireframe to see the paintable vertices easier. In tool settings, there's a symmetry option, which is the same as the one up here. This will basically mirror your paint strokes. To smooth your weight paint a little, drop down the weights drop down and click smooth. And once the model is properly weight painted, we can create some easy to use controls, which is where rigging really comes to life. There is no right or wrong way to create controls as long as they make all the required movements possible and simple to animate. So I'm just gonna show you a bunch of useful ones and you do with that what you will. Okay, let's make an IK handle. An IK handle is a control on the rig which dictates the endpoint of a bone chain. In order for it to work best, it also requires a pole vector so it knows which direction to make the bends. So to create the IK handle, I'll extrude this bone out, so both the bone heads are in the same place. Then I'll make the bone disconnected, remove its parent in the bone properties tab, and rename it. Now because this is a controller bone, it's not actually binded to the mesh and it's not going to deform the mesh, I'm going to tick off this deform option. This is just for optimization and for when you're exporting this rig into other softwares, but it's a good practice to have, so turn it off. For the pole vector, I'll extrude the bone from the bent joint, also disconnect it and remove its parent, rename it, and bring it out in front like so. Then also turn off the deform. Turn it off. We now have the required structure to make the IK controls. Hop into pose mode and select the bone pointing into the IK handle. Now open the bone constraints tab. This is where you create different constraints, rules, and conditions for the bones, which can make really smart control systems. Click the drop down and add an inverse kinematics constraint. For the target, pick the current armature, and for the bone, pick the IK bone. If the IK bone doesn't work, just move the middle joint forward a little so it knows in which direction it has to bend. I've had similar issues before and I look like a total idiot. I don't get it. I don't understand. What is wrong? Technically, it should work now, but we're not done yet. For the pole target, also pick the armature, but for its bone, pick the pole vector bone. Your bone chain might flip around, so just mess with the pole angle until it's pointing back where it should, and also set the chain length to the amount of bones you want to be affected by this. In my case, that's 2, so the shin and the femur bone. So now the IK handle will move the endpoint of the leg, and the bend will always point towards the pole vector. You've got perfect control. However, the foot is now rotating with the shin. We don't want that. Let's make it so that we can control the rotation of the bone with the IK handle as well. In edit mode, disconnect the foot and remove its parent. Then in pose mode, give it a child of constraint and make the parent the IK bone. The foot is no longer affected by the shin, but it's instead mimicking the IK handle bone. So the IK handle moves the leg and it also rotates the foot. This is a complete leg rig if you ask me. However, people usually set up FK to IK switches. That is a little bit more complicated and I can make a separate tutorial on it if you want to, or you can just watch one of the many already available sources out there. Let me know in the comments or join my Discord server so you can suggest and vote for my videos. This one was voted. There are also a lot of other useful constraints, such as copying different attributes, limiting transfer transformations, volume preservation, stretching or tracking to different objects or bones, or so much more. This is something I encourage you to play around with, see what they do, and then try to incorporate these tools into your rigs.
My brain is getting fried. Right, my brain is getting fried. I need to actually do stuff. Shift E. Right. Um, 7.7.45. Um, 5, negative 0.75. Does this not have a dotted line? Hmm. Hmm. Then it's seven, 8, 5. Here. Now is the armature mirroring again? Spin binding, rigid rig, pinning, armatures.
Having the tail there makes it easier to visualize. In Blender, press Shift and A to add an armature, and this thing you see in the viewport is a single bone. We can make a simple bone hierarchy by hopping into edit mode, selecting the head or the tail, and extruding it to build the tree. You can change the bone's parenting or connected attributes in the bone properties panel in the relationships dropdown. If you want to preview how the hierarchy works,
Hmm. I don't know if that's going to be bad. Doing anything is difficult. Why life like that?
You can't do that in edit mode. This is where you set up the skeleton. You need to hop into pose mode by pressing Ctrl and Tab or visiting this drop down up here. This is where you get to move, use, and animate your rig, and you can see exactly how your bone chain works based on the hierarchy you've set up. Okay, but how do you actually assign geometry to it? Well, that depends on what you're rigging. First, we need to talk about skinning. Skinning is a process of assigning the influence of each bone on the rig to individual vertices on your model. The values go from 0 to 1, where 1 is full influence, 0 is no influence, and the values in between are partial influence. It's easiest to depict as a gradient. Any vertex can be affected by as many bones as you want, as long as all the influences add up to 1. Usually that influence, or that weight, is painted by a brush. That's why this process is called weight painting. We know two approaches to skinning. On one hand, we have rigid or separate type of skinning, and on the other hand, we have bendy/deforming. I'll explain both, and I'll rig my own character in the end to put everything into practice. First up, we've got rigid type of skinning, which is the simpler of the two. Rigid skinning is used when your character is made up of multiple objects and none of them deform. They just move along and rotate. You'll often see these kinds of rigs on robots. The way you do this is by hopping into pose mode on your rig, selecting the bone you want to parent to, and then hop back into object mode. That bone is still technically selected, so now you can select your object, or multiple objects. Then select the armature last, so the armature is the active selection. Press Ctrl P to parent, and select bone. So all these objects are now parented to the selected bone. Alternatively, you can select all of your objects, then select the armature last, press Ctrl P to parent, and then pick Parent to Armature with empty groups. Technically, all these objects are now parented to the armature, but they're not assigned to any bone, so far nothing happens. Now, however, the objects receive new vertex groups in the Object Data Properties tab, and those groups have the same names as your bones. Here's another reason to keep your bones nicely renamed. I always say organization. It makes things so much easier. Now you can select all the objects, hop into edit mode, then select them with the L shortcut. Then in the vertex group, select the bone you want to parent your selection to, make sure the weight is set to 1, and click Assign. You've technically weight painted this entire object to that bone by giving it a value of 1, so now it's going to move with it. There's much more visual ways to weight paint, and we'll do that in a second.
I need to... bones. Oh, okay. No wonder I'm having difficulty. There's so many... Select mirror. Shift Control M. Shift Control M. Control C. Control C. Shift Control M. it's mirroring on the... It's mirroring on the x-axis. And everything. No. Everything. Rotate Z 90. X-ray. Tab. Shift Control M. No. Shift Control M. Never mind. Control C. Oh. My hair is barely green anymore.
Show you this. Once you do this for every object, you should have a rigid rig that moves the parts around without deformations. If you want deformations though, you need to do weight painting, which I mentioned before, which is where bendy skinning comes into play. As mentioned before, weight painting is a method of assigning weight to different vertices on your mesh to the bones on the armature to ensure proper and wanted deformation during the animation. That was a heckin' rhyme I did. This bone will affect these vertices by this much, and that bone will affect those vertices by that much. Again, we sort of did that in the previous step. We just assigned the maximum weight to full objects. Now we're just gonna do it with a brush. Okay, assignment time. To rig this guy, first make the middle row of bones, starting at the crotch, so that's our main root bone, and rename all of them. Now make one of the sides and rename that as well. Select all the bones on the sides and press Ctrl and F2. Since F2 is a shortcut that renames things and Ctrl and F2 is a shortcut that batch renames things, it makes sense. Set this box to selected and bones. Set the type to set name and the method to suffix, meaning it will add something at the end of the word. That's what a suffix is. Put the name to .l, which will add a dot.
I need more controls rather than this fast-paced stuff. I don't... Nobody can learn when everything is so fast. animation rigging. Oh man, I'm gonna have to read all of this. Oh man, how boring is this going to get? As boring as it needs to be. Okay. We're bringing it big. We're bringing it big. We're forgetting what we're already doing. The apartment I live in is so deep. The floorboards aren't even level. Nothing is great. Nothing's great. Nothing's good. I'm in hell. I'm in hell. Everything triggers my autism. Everything triggers everything. I don't like living, but I live in spite. I'm not gonna let it win. Not gonna let life win. I live. Okay. Introduction. Animation is making an object move or change shape over time. Yeah, no shit. Objects can be animated in many ways, moving as a whole object, changing their position, orientation, or size in time, deforming them, animating their vertices or control points, inherited animation, causing an object to move based on movement of another object, its parent, hook, armature, etc. In this chapter, we will cover the first two. The basics given here are actually vital for understanding the following chapters as well. Animation is typically achieved with the use of keyframes. Wonderful. Wonderful. Related sections: physical simulation and motion tracking. Cool. Motion tracking is cool. If only I can do motion tracking, but I have no ability to do anything because I am stupid and I know nothing. State colors. Okay, properties have different colors and menu items for different states. Gray, not animated. Yellow, keyframed on the current frame. Green, keyframed on a different frame. Orange, changed from the keyframed value. Purple, controlled by a driver. The changed value highlight currently doesn't work with NLA. I don't know what any of that means. Rigging. Rigging is a general term used for adding controls to objects, typically for the purpose of animation. Rigging often involves using one or more of the following features. Armatures. These allow mesh objects to have flexible joints and is often used for skeletal animation. Constraints. To control the kinds of motions that make sense and add functionality to the rig. Object modifiers. Mesh deformation can be quite involved. There are multiple modifiers that help control this. Shape keys. To support different target shapes, such as facial expressions, to be controlled. Drivers. So your rig can control many different values at once, as well as making some properties automatically update based on changes elsewhere. Rigging can be as advanced as your project requires. Rigs effectively define a user interface for the animator to use without being concerned with the underlying mechanisms. Examples: an armature is often used with a modifier to deform a mesh for character animation. A camera rig can be used instead of animating the camera object directly to simulate real-world camera rigs. With the boom arm mounted on a rotating pedestal, for example, such effects such as camera jitter can be added. The content of this chapter is simply a reference on how rigging is accomplished in Blender. It should be paired with additional resources such as Nathan Beckman's excellent introduction to the fundamental concepts of character rigging. Huh. Hold up. This guy's a Clippy. Clippy's together strong. What this? Hold on. What this? 14 years ago? That's pre-AI. I love this.
Main rigging DVD. My name is Nathan Vegdahl, and on this DVD, I'm going to pretend to know something about rigging. So let's get started, shall we?
Love this guy already. Oh. Hold on. My watch isn't on my wrist. You mean to tell me that the Blender manual had a frickin' link to this guy's videos and reading the manual is cool, actually.
The first thing I want to do is just look at rigging from a bird's eye view. Broadly speaking, when we build a rig, we're actually building a tool for someone to use. And because of that, usability is one of our primary concerns as riggers. It's much like how software developers ought to keep usability in mind. They could write an amazingly powerful piece of software, but if it's a complete pain to use, it's not really that useful to most people. Rigs are the same way. You could create the most amazingly clever rig with perfect deformations and simulation, but if it's hard for animators to use, it's nothing but an exercise. It's not actually useful for real animations. So remember, rigs are tools for people to use. Rigs are a means to an end, they are not an end in themselves. Because of that, I highly recommend that if you're serious about rigging, that you take up animation as well. You can still become a good rigger without doing that, especially if you work closely with the animators that do use your rigs, but it's going to be a lot trickier. If you do animation yourself, it's a lot easier to immediately understand why some rigs suck and some rigs rock. So with that out of the way, what can you expect from this DVD? Well, this DVD focuses almost entirely on building good control schemes for animators. If you're looking for material on creating great deformations or setting up simulations, well, you've got the wrong DVD. But wait, please don't throw this in the trash. Seriously. Even if you just want to learn deformations, this DVD covers a lot of prerequisite material for that. And that's because this DVD does not approach things from a purely step-by-step vantage point. Instead, I've put a lot of effort into teaching the fundamental concepts behind rigging and how to use them to do your own problem solving. Imagine, if you will, a book on computer programming that tries to teach you how to write every possible piece of software you will ever want to write.
Yep, I definitely read a little bit of a book on computer programming. I got 6 chapters in, and then it's just like, wow, I know enough to know that I know nothing. This is great. Story of my life, learning just enough to know that you know nothing.
Step by step. It would be ridiculous. It's not possible. There's too many things a person might want to write. Instead, a good programming book will teach you concepts that you can use to solve a lot of problems. The same applies to any skill, in fact. Step-by-step drawing books aren't that useful either, except perhaps if you're just taking your first baby steps. But ultimately, you'll need to learn how to think about and approach drawing. And a good drawing manual will try to teach that. I am taking that same approach here. A lot of the material on this DVD isn't even specific to Blender. I will be using lots of examples, of course, but they are all in the service of trying to teach concepts and teach you how to think for yourself and solve your own problems. And I hope that you will approach this DVD in that same spirit. If there is a rig that you want to build, but which is not covered on this DVD, I really encourage you to approach it as a learning opportunity and try to figure it out for yourself.
Oh.
That is how you will really learn rigging. Rigging is a lot more about creative problem solving than it is about setting up specific rigs. This DVD has been a project of passion for me, and I hope you get a lot out of it. And since it's released under Creative Commons, I really encourage you to make copies of it and share it with other people.
Oh yeah.
Keep it to yourself. Although it would of course be nice for people to support the DVD too, if they can, but don't worry too much about it. So anyway, let's get on to the rigging now. If you're already familiar with the basics of Blender's rigging features, you can probably skip this video.
Okay,
I'm just going to give a brief overview of the main features relevant to this DVD. The simplest rigging feature in Blender is called an empty. In other software, this is sometimes called a null object. An empty is an object that has nothing in it. No mesh, no curves, no materials, no nothing. All it is just a location, rotation, and scale in space. That might not seem so useful, but we will see in the rest of this DVD that in fact they are quite useful. Closely related to empties are armatures. Armatures also do not contain meshes or anything else that is renderable, but they do contain bones, which themselves are a lot like empties in many respects. Bones are essentially just transforms in space as well. Did I just say transforms? Yes, I did. In computer graphics, a transform is something like a rotation, location, or scale, or a combination thereof. This will become clearer in Chapter 3. Anyway, one of the strange things about armatures in Blender is that they're kind of like their own little world. In fact, armatures even have their own internal layer system, and an armature's bones can be put on different layers within it. It's kind of weird, but you'll get used to it. Armatures and empties are the primary means by which we will construct the framework and controls for rigs. Next up, we have drivers and constraints. Drivers allow us to set up relationships between arbitrary properties in Blender, and constraints allow us to set up relationships between objects' transforms. In my head, I tend to think of drivers and constraints as being related, because they both allow us to automate things in a rig. But I guess that's a little arbitrary, since ultimately, everything we do in rigging is a form of automation in a sense. Still, I like to think of these as the automation features in Blender's rigging toolbox. Surprisingly, empties, armatures, constraints, and drivers are pretty much all we're going to be using on this DVD. It doesn't sound like much, but you can put them together in really amazing ways to do really cool things. I mean, just think of all the things that can be made from protons, neutrons, and electrons, right?
Oh yeah.
Huge possibilities. Now for a few tips and tricks that I use a lot while I'm rigging. first thing is hotkeys. Hotkeys are great and will speed up your workflow a lot. I do my best to mention hotkeys the first time I use them on this DVD, but if I forget one, you can usually find them in the header menus. Besides which, hotkeys in Blender sometimes change between versions, so for all I know, you're watching this at a time when Blender has an entirely new default key map. So
A lot more than just the default key map.
Also, you can call up the operator search menu at any time. At the moment, the hotkey for this is spacebar. If you press spacebar at any time, the little search menu will pop up, and you can search for any command by name. To execute the command, just select it from the search results.
No, spacebar actually pauses and plays the animation now, doesn't it? Hold on. Hold on. What does spacebar do? Yeah, that pauses and plays the animation frames. Okay. Would it be Shift A? Add. No. Nope. I don't know.
You can choose it with the mouse. With this feature, hopefully you will never get lost. If you're watching with this, use the up and down arrows to execute. The little search menu will pop up, and you can search for any command by name. To execute the command, just select it from the search results. You can use the up and down arrows to choose it, or you can choose it with the
A lot
mouse.
has changed in Blender, but I'm going to take this as is.
If you're watching this DVD, you really should already know the next bit, but just in case, I want to point out that you can do mode switching via this menu here. Sometimes the hotkeys for mode switching can be confusing, especially with armatures, so you can always do it from here if you need to. Next, I almost never use the transform widgets. Instead, I use the G, R, and S hotkeys to grab, rotate, and scale things. The seeming downside to these hotkeys is the matter of restricting the motion to specific axes. But that turns out to be pretty easy. While you're in the middle of grabbing, rotating, or scaling something, you simply press X, Y, or Z on the keyboard to restrict it to that axis. By default, it restricts the motion using world space axes, but if you press one of the keys twice, it will restrict it in the space selected in this menu, which I usually have set to normal. If we want to clear out the transformations on something, we can use Alt-G, Alt-R, and Alt-S to clear the location, rotation, or scale of our selection, respectively. I do this a lot throughout the DVD when I want to move something back to its default position. Something else I do a lot on this DVD is move things with snapping turned on. To do that, simply hold down Control while you move something. I mainly use this when I'm dealing with lots of overlapping things. I'll move some things off to the side with snapping on, and then later I move them back with snapping on as well. That way they go back to exactly the same place. There are different snapping modes though, which you need to be careful about. When I'm rigging, I always have it set to increment. Increment moves things in, well, increments. It doesn't snap to grid spaces, it moves things in grid-sized increments, which is an important difference, and it's what makes it useful for temporarily moving things out of the way. Lastly, there's this weird thing here. This is called the 3D cursor, and it's one of Blender's more unique features. It's basically just a position in space that Blender can use for various purposes. You can place it wherever you like by simply left-clicking. One thing Blender uses it for example, is as the point to create new objects at. If I add another monkey head now...
Wait, hold on.
Cursor. Another use for the 3D cursor...
Pause, hold on. My tea. I forgot about my tea. It's been 2 hours and I forgot about my tea. It's not cold, but it's not warm. Hold on, let me copy this and let me put the link into the chat. And this is what I'm watching. And it's good. It's awesome. It's 14 years ago. It's the sacred texts. The sacred texts.
Rotation or scaling. Normally, Blender rotates and scales around the average position of your selections, but you can change that. If you select 3D cursor from the pivot point menu, now they pivot and scale around the 3D cursor. The 3D cursor can also be used to help snap things to certain positions, but I'll get to that later in the DVD. Finally, I just want to note that this DVD has been a long time in the making, so the videos actually span several versions of Blender. There haven't been any major changes to the rigging tools covered on this DVD during that time, but just don't be too surprised if the organization of a panel changes during the DVD or something like that. So with that in mind, let's start our first rig. Our first rig is going to be very simple, a bouncy ball rig, hence the ball on the screen. So the first problem at hand is to figure out what features we want the rig to have, and that depends on how it's going to move. In this case, let's say that the ball is going to be used in a simple 2D cartoon, with no sense of 3D whatsoever. Immediately, that tells us some things about how the ball is going to move. The most obvious is that it isn't going to be moving in 3D. It will only be rotating on one axis, and it will only be moving up and down and left and right. No depth, no 3D rotations. Whew. And that will make our lives easier. But it's also a cartoon, and that means squash and stretch. So all of this means we need to develop a rig that makes it convenient to move, rotate, and squash and stretch the ball in 2D. The simplest way to do this is to simply use the ball object itself as the rig. So let's try that. So the first thing we want to do then is lock one of the translation axes of the ball so that it can only move in 2 dimensions. To do this, we need to go to the N panel in the 3D view. You may need to press N to toggle it on. We also need to select the ball. Now we can find the ball's transform panel, and toggle it open if necessary by clicking on it. You can also find the same data organized a little bit differently in the object properties. I prefer to use the N panel most of the time because it's more convenient. But the object properties panel is actually the official place to look at and modify an object's properties, so keep that in mind. Now we need to figure out which axis to lock. So let's rotate our view slightly and play with the translation axes to see which one we want to lock. Aha! We want to lock the y-axis, because in this case, that's the forward-backward axis. And we only want the ball to move from side to side and up and down, not forward and backward. To lock it, simply click the lock icon next to it to toggle it on. Also, let's zero it out. Left-click on the field and type in 0. Notice now, when we grab the object, it doesn't move on the y-axis. However, we can still modify it by typing in values like we did earlier. So it's not strictly locked, but what it does is this prevents the animator from accidentally moving the ball on the y-axis in the 3D view. We're now going to do the same thing with rotation axes, but in this case, we're going to lock 2 of the axes, not just 1. So let's figure out which axis we want to be free. Go to the front view and simply rotate the ball. We can see in the transforms panel that we're rotating on the y-axis, which means that's the rotation axis that we want to be free. So let's lock the other 2. And now we can only rotate the ball on its y-axis in the 3D view.
Awesome.
So now we have a ball that's limited to moving in 2D space. We can only translate and rotate in that 2D space, so that the animator doesn't have to worry about accidentally moving it in an unintended way. But we still need squash and stretch. Now we could put the onus for this on the animator. The animator could simply manually scale the ball on different axes like this. But we can make the animator's job a lot easier than that. Why not have the ball automatically squash and stretch when the animator scales it? To do this, we first want to choose an axis for that squashing and stretching to happen on. In this case, the z-axis seems like a good choice. And we want to lock the other two axes so that the animator only has to keep track of animating that one axis. Now when we scale the ball, it sort of looks like squash and stretch already. But we still need it to expand and contract on the other axes. And there are two different ways that we can do this. We can either use drivers, or we can use constraints. In this case, drivers would give us more control over exactly how the ball behaves, but constraints are a lot easier. To keep it simple, we're just going to use constraints for now. And happily, Blender has a volume preservation constraint that forces whatever object is applied to preserve its volume when it scales. We can add a constraint to the ball in two ways. The first is to go to the constraints panel. Make sure the sphere is selected, and from here, we can click on the Add Constraint menu and add the Maintain Volume constraint. You'll notice that a new panel appears that represents the Maintain Volume constraint. In fact, any constraints on the currently selected object will show up here as a panel, and this is where you manage the constraints on an object. So, for example, you can delete any constraint on an object by clicking on the big X here. The other way you can add a constraint is with a hotkey in the 3D view. Make sure the sphere is selected, and press Ctrl-Shift-C. The constraints menu will pop up, and from here, we can select the Maintain Volume constraints. And ta-da! It's been added, just like the other way. And we can also see it in the constraints panel. Adding it this way is no different in terms of the end results.
Hold on. Not to pause or anything. Not to pause or anything. Object. Object modifiers. Hold on. Constraint. Maintain volume constraint. Transform constraints. Location constraint, location. Transform constraints. Okay. Oh, okay, there's constraints. Okay. Okay. Constraints. Okay. Figured out where they moved it. Okay. Yes. No, that is the classical music. I don't need the classical music. I need to get back to my humane rigging DVD. I'm the bonus features.
Have parameters that you can tweak to make them behave in different ways. In this case, the maintain volume constraint has a parameter at the top labeled free, and that's the one that we care about. This tells the constraint which axis the user is going to be scaling, so that it knows to scale the other two axes automatically. In this case, the user is going to be scaling the z-axis. So, let's select that. Now if we scale the ball, it squashes and stretches. Yes! So much easier for the animator. Congratulations! You've made a simple bouncy ball rig. However, while this rig was simple to create, it turns out that it's not ideal. This ball rig can do some pretty cool things, like bounce across the screen with some nice squashing and stretching. However, if we want it to roll while it's squashed or stretched, it really can't do that. And this is because the axis of squash and stretch is inexorably linked to the rotation of the ball. We can't rotate the ball without rotating the squash and stretch too. Clearly, this isn't optimal, but how do we unlink the squash and stretch from the rotation? As with many rigging problems, there are actually multiple ways to do this, but I'm going to focus on one in particular, because it also gives me a great opportunity to introduce one of the most basic rigging tools in 3D graphics, parent-child relationships. Right off the bat,
Hell yeah.
parent and child, we think of two separate independent people who have a certain relationship to each other. But to explain what a parent-child relationship is in computer graphics, I think it's actually easier to think of it in terms of a pregnant woman who has yet to give birth.
Okay.
And if you drop a piano on the mother, squishing her, the child gets squished too. But the child can still move inside of the mother's womb as well. Mind you, I'm not intending to make legal statements here. It's an imperfect analogy anyway, but it's just to give you an idea. So let's actually test this out in Blender now. We already have a ball, so we just need one...
Oh man. Oh man. The 14 years ago was a different time entirely. Oh my gosh. I was like, man. I was like 10 when this guy was making videos. Like where was this absolute comedian growing up? I love older internet. I love older internet. It's great.
more objects to be able to create a parent-child relationship. In this case, let's create a cube. And let's place the cube so that the ball is inside of it. And switch to wireframe view so that we can still see the ball. Okay, so now we can think of the ball as being the baby, the child. And we can think of the cube as being the parent, or the mother. But we have to to explicitly tell Blender to create this relationship. And to do that, all you have to do is first select the ball, then the cube, and hit Control P. And then a menu will pop up with only one item in it. I'll explain why there's a menu at all later on in the series. And just click on that one item in the menu, confirming that you want to create the parent-child relationship. Now, it doesn't look like anything much has actually changed, but let's select the cube and move it. Hey, look, the ball goes along with it. But what about moving the ball? Ah, the ball can still move independently as well. But what's really going on here? So what's going on is that the ball exists inside the, quote, space of the cube, similar to how a baby exists inside the space of its mother. What this means in 3D graphics terms is that the translation, rotation, and scale of the ball are now all relative to the translation, rotation, and scale of the cube. To better illustrate this, let's try rotating the cube, and then playing with the ball's translation axes. You'll notice now that when we change the ball's X position, it's actually moving along the X-axis of the cube, not the X-axis of the world. In essence, the cube is now the ball's world. But it gets even weirder. If we scale the cube on just one axis, not only does the ball squish as well, but the meaning of its translation axes squish too. So notice that it moves further on the long axis than on the short axis for the same value change. This is because the ball's very world, its parent, its mother that it is inside, has been squished. Just like a piano. Wait, there's more. What if we rotate the ball? Oh my goodness, how cool is that? The ball can still rotate in this distorted space. And this, my friend, is exactly how we're going to accomplish our goal. However, before we do that, I just want to point out that parent-child relationships can also be multi-level. So if we create another object, we can give the ball a child as well. And
Oh, okay.
at this point that the pregnant mother analogy kind of gets disturbing because now there's a pregnant
No, it's a turducken.
baby.
No, turducken. No, forget about the pregnant lady, it's a turducken. No, don't.
Oh, maybe I should drop that analogy now.
Yeah.
And back to the ball rig. We now know that we can accomplish what we want by using parent-child relationships. However, using a cube really isn't ideal, because it obscures the ball. In fact, we really don't want the parent to be an object with any visible mesh at all. And this is where empties come in. Remember empties? They're objects that contain no mesh, or, in fact, any other data at all. They're just transforms in space. And that's exactly what we need. So, let's delete everything except the ball. And let's add an empty. Now, if we were to move the empty to the center of the ball, as we want to, it would become hidden within the ball, and we don't want that. We still want to be able to see it. Fortunately, Blender allows us to change the appearance of empties. To do this, select the empty in question, and go to the empty properties panel. This sounds kind of funny, empty properties panel. Like it's empty, but it's not empty, it's just properties panel. Anyway.
Yeah.
And select cube. Yay! Now it looks like a cube. And it's a cube that's large enough to be outside of the ball when they overlap. If it wasn't large enough, we could increase its display size using the size field below the display menu. So now clear the empties transforms to place it in the same position as the ball. And let's make the ball the child of the empty. Now the empty is going to be responsible for the squash and stretch and location of the ball. So let's set it up for that, like we did with the ball. Lock the Y translation axis and the X and Y scale axes. And add the maintain volume constraint to the empty. And configure the constraint. The empty will also be rotating, however, to determine the direction of the squash and stretch. So let's also lock the X and Z rotation axes. Now we can move, rotate, and scale the empty. And we can spin the ball. Much nicer. However, we also need to go and clean up the ball because it's no longer responsible for translation or squash and stretch. So let's completely lock its translation and scale axes, and its maintain volume constraint is no longer necessary. So this is pretty cool now. We can spin the ball, even in its squashed or stretched states, and that enables a lot more animation possibilities. However, there is still one last thing that can be improved, and that is to remove the need for the animator to counter-animate. Wait, what? What do I mean by counter-animate? Okay, so counter-animation is an issue that comes up in a lot of parent-child rig setups. In this case, if the animator wants the ball's spin to remain stationary, but still wants to change the direction of the squash and stretch, she would have to first rotate the empty, and then rotate the ball back to compensate. And over the course of an animation, the animator would have to do this over many frames, compensating for or countering the rotations of the empty. That process is called counter-animation, and it's bad. Bad, bad, bad. It is unnecessary work, and it distracts the animator from their job, which is making good animations. So, we want to design and build our rigs to avoid this. In this case, what we want to do is find a way for the ball to follow the translation and scale of the empty, but not its rotation. Right off the bat, I want to let you know that there is a really easy way to do this if we were using bones. In fact, it's a simple checkbox that you just uncheck. But first of all, this option doesn't exist on objects, and second of all, even on bones, there are some pretty good reasons to avoid using it in favor of other methods. So let's figure out another way to do this. To get the thinking started, let's revisit what it is that the animators would do without this. Animators would, by hand, be rotating the ball in the reverse direction of the empty to compensate for the empty's rotation. So, why not just think of this as a problem of automating that process? Automating what the animator was going to do anyway, just rotating the ball in reverse of the empty. And it turns out Blender has a great tool for exactly this sort of thing, which I briefly introduced in the last video, and that tool is called drivers. So what we want to do is create a link between the empty's rotation and the ball's rotation that drives the ball's rotation in reverse. Now, creating drivers is a little annoying, and it's going to introduce a new component of Blender's UI called the graph editor, but I'll try.
I'm about to sneeze. This is where I need to keep tissues next to me. I didn't make it. I didn't make it. Anyway, here we go.
Keep it simple for now, and just explain the parts that are relevant to this problem. I'll get more in-depth into the driver system later on. First, how and where do we add a driver? On a technical level, drivers are essentially just automated animation. So drivers exist on the property that's going to be automated, or in Blender's terminology, the property that's going to be driven. In this case, that's the ball's Y rotation. To add a driver, you simply right-click on the property you want to drive and select Add Single Driver. Notice that the property changes color. This color indicates that the property is automated, that it has a driver on it. However, there is a problem now if we try to rotate the ball, which is that we can't rotate it. And this is because drivers completely take over the property that they are automating. But we still need the animator to be able to animate the ball's rotation. So how can we solve this? It turns out that this sort of situation is actually really common in rigging. You want to automate some aspect of an object or control's motion, but you also still want the animator to be able to animate on top of that automation. This problem is really common in rigging, in fact, so it would be a good idea for us to find a general solution for it. And it turns out there is in fact a very general solution for it. Parents! Remember
Yay!
Yeah, if an object has a parent, it exists in that parent space, and therefore it moves with the parent, but it can still move independently as well. So whenever you run into this kind of situation where you want something to be automated, but you want to be able to animate on top of it as well, you can simply give the object a parent and use that parent to automate the motion. So let's add another empty to be that parent. And let's increase its display size so that the ball doesn't completely hide it. Let's now switch the ball's parent to be the empty we just added. Now the ball follows that empty instead of the main control empty. To make the ball still follow the main control empty as well, we can simply parent the new empty to the old one. Now you can see that if we want to compensate for the rotation of the main control empty, we can do it on this new empty. Whew. Okay, this is actually getting kind of complicated, and all just for a 2D ball rig. But we're almost there. Worry not. Worry not. Select the new empty and add a driver to its Y rotation axis. By default, the driver isn't set up to do anything. We have to tell it how we want it to automate the property. To do that, we need to go to Blender's graph editor. Let's split the 3D view into two windows. Right-click on the edge and select Split Area, then move the mouse about halfway in the middle and left-click. Now change the window type of the left area by clicking this icon in the lower left, and select Graph Editor from the menu that pops up. Not to get off track too much, but that's how you can customize your window layout in Blender.
Wonderful.
Now that we have a graph editor visible, we need to change it to driver mode so we can see the drivers in our scene. Click on this menu here and select drivers. Now, in the left pane of the graph editor here is our list of drivers. Currently, there's only one. Click on it to select it. To configure it, we need to see its properties, which are in the graph editor's N panel. So press N on the keyboard to toggle it open. This looks really confusing, and, well,
yeah.
It is. But let's simplify. The only panel we care about in here is the drivers panel, so collapse everything else. Okay, that's better. So this shows us the properties of the currently selected driver. There are basically two parts to this panel. The bottom part here is where we tell the driver what other properties are used to automate this property. And we call those properties the variables of the driver. You can add as many variables as you want by clicking the Add Variable button. But in this case, we really only want one. There are also multiple variable types that you can choose from via this drop-down menu, but let's not get into that yet. For now, leave it as transform channel. Let's configure this variable to reference the y-axis rotation of the main control empty. First, we need to specify the object, and in this case, it's the main control empty. The field here is where we do that. We can either type in the name of the object manually, or we can treat the field as a drop-down menu and simply select the name of the object. Now all we need to do is select which transform channel we want to reference on the main control empty. In this case, we want the y-axis rotation. And that's all for the variables. But the driver still isn't going to do anything yet. We need to configure how it's going to use the variable to automate our property. And that is what the top section of the driver panel is for. There are multiple different modes that a driver can be in, which influences how it uses the variables. By default, it uses scripted expressions, and we're just going to stick with that for now. I'll explain the other modes later. In scripted expression mode, the driver evaluates the Python expression in this field. An expression is simply a math formula, and we can use any of the variables we've created for the driver in that expression. In this case, we only have one variable, and it's named var. We can change the name if we want, but I'm going to leave it. What we want to do is have this driver do the opposite of what our variable here does.
So multiply by negative?
Will rotate opposite of the main control empty. So the expression we're going to use is simply negative var. After changing the driver, it's a good idea to click Update Dependencies, just to make sure the changes take properly. Now if we rotate the main control empty, the new empty and the ball appear to stay stationary. But let's take a look at the rotation values of the two empties. The main empty has a rotation of 30 degrees right now, and the new empty has a rotation of negative 30 degrees, exactly the opposite. And that's why it appears to be remaining stationary, because it's doing exactly the opposite of whatever the main control empty is doing. And because the ball is its child, it too remains stationary. And in this way, we have automated the counter animation process. Hooray! Since the new empty isn't a control that we want the animator to be using, or that the animator in fact needs to use at all, let's move it to a hidden layer. Select the empty and press M on your keyboard. Click on this layer. Objects and bones that the animator doesn't need to use, but only act to automate something, are what I like to call mechanism objects, or mechanism bones if it's a bone. It's like the internal parts of a car. The person driving the car never directly manipulates them, but they're still part of how the car functions. Okay, and lastly, let's name the main control empty something other than empty. Perhaps main is a better name. And naming your objects and bones something recognizable and sensible is actually a really important part of rigging, so never forget to do that. Now we can finally play around with our rig.
Hold on. Did I forget to do that? I think I forgot to do that. Yeah, I forgot to do that. I forgot to do that. X-ray tab. Pelvis. Pelvis. Body. Head. Arm. Dot left. Larm. Dot left. On dot left. Up leg dot left. Low leg dot left. Foot dot left. Cool. Now, if only I knew how to mirror the bones onto the other side. Okay. There we go.
In the previous video, we figured out how to rig a 2D bouncy ball using empties. In this video, we're going to recreate that rig, except we're going to do it with an armature. But why? Why go through that effort? Well, to be honest, we should have rigged it with an armature to begin with.
Oh, okay.
Steps one at a time.
Okay.
Armatures are a large and complex topic. So to start off, let's take a brief look at the advantages of using armatures, and why we would want to use them for rigging. The most obvious reason is actually one that doesn't apply in this simple case, but I'll point it out anyway. Blender has an armature modifier that allows you to deform meshes with multiple bones, and Blender has no such modifier for multiple empties. Again, this isn't relevant to the 2D bouncy ball, but it becomes important when we start rigging characters with contiguous deforming meshes. Another reason to use armatures is that they give us a lot better control over the transform spaces of our controls and rig mechanisms. So, for example, it's trivial to set a custom zeroed out position for a bone, whereas that's much trickier with objects. And this control over bone spaces turns out to be important, as we'll see later on. Another reason to use armatures is that there are some important constraints that are only available for bones, such as the inverse kinematics constraint. There are also two production-oriented reasons for using armatures, which don't really apply so much if you just plan on building and animating a rig in one blend file, but they're very important in a larger production with multiple scene files. The first of those is that Blender's animation data is stored in something called actions. Whenever you animate an object, that object gets an action that stores its animation data. Unfortunately, if you have 50 rig controls that are all separate objects, that means you're going to get 50 separate actions when you animate them. And that is not only an organizational nightmare, but it also makes the animation nearly useless for Blender's nonlinear animation system. If you use an armature, on the other hand, the whole armature just gets one single action. The second production-oriented reason for using armatures is that armatures are the only object type in Blender that you can still fully manipulate if you link it into another scene. If you plan to use the same character rig in multiple scenes, that's kind of important. You don't want 50 copies of the same rig for 50 scenes, you just want the scenes to all reference the same rig and put different animation on it. Armatures are currently the only way to do this in Blender. So that, in a rather large nutshell, is why you want to use armatures to build your rigs.
The biggest nutshell.
Objects that contain something called bones, and these bones are kind of halfway between being like vertices and edges and being like empties. Bones can be edited in a similar fashion to meshes, but they can be posed in a similar fashion as objects. In short, they are a confusing conundrum, but let's see if we can—
Yay, confusion!
actually using them a little bit and demoing how they work. To start, let's add an armature. By default, an armature starts with one bone. To edit the armature and add more bones, we have to go into edit mode, so hit tab. In edit mode, we can select the bone's endpoints, which are kind of like vertices, and move them around. We can also select the whole bone and move it around, but in edit mode, bones are defined by the locations of their endpoints. While in edit mode, we can also add more bones to the armature by hitting Shift A. In short, edit mode is where you add and place bones in the armature. To use these bones for animation, however, we need to go into pose mode. To do that, hit Control Tab. In pose mode, the bones no longer behave like vertices or edges. Now they behave a lot like empties. Instead of being defined by the position of their endpoints, they are now defined by transforms: location, rotation, and scale, just like empties. In pose mode, you can also lock bones transforms, just like with objects.
Okay.
And you can add constraints, also just like with objects. In short, in pose mode, bones behave like objects. The only object-like thing that you can't do in pose mode is parenting. To parent bones to each other, we have to go into edit mode. Notice that with bones, the parenting menu has two items: connected and keep offset. Keep offset is the normal parenting behavior that you're used to with objects. So let's select that for now. I'll explain connected later. Notice that parenting has no effect on the bones in edit mode. You can still move a bone's endpoints around freely without causing the bone's children to move with it. But if we switch back to pose mode, then suddenly the parenting has the expected effect. You might wonder why edit mode exists at all, and you would be smart for questioning that. After all, why not just let users add and parent bones in pose mode? The main purpose of edit mode is actually to determine the default rest positions of the bones. So for example, if I select this bone here, we can see that all of its transforms are completely cleared, and yet it's not at the origin position, nor does it have cleared rotation. That's because of how we positioned the bone in edit mode. Wherever a bone is placed in edit mode, that is its default zeroed out position. And this is useful for several things, not the least of which is allowing the animator to clear transforms on rig controls without worrying about it collapsing the whole rig to the origin. So that's a basic overview of armatures. And with that overview out of the way, let's dive into rigging the ball with an armature. The process is going to be almost identical to how we did it before, except we just need to be mindful of edit mode and pose mode. Therefore, I'm going to glaze over the stuff that we've already covered and focus on what's different. Let's start by adding an armature for the rig. Make sure its transforms are cleared, and name the armature rig. Also, we want to be able to see the bones inside the ball as we're working on the rig. We could switch to wireframe, but I prefer to set the armature's draw type to X-ray. Go to the object properties, find the display panel, and toggle on the X-ray checkbox. Yay! Now we can see the...
Okay, hold on. Okay. Armature. Object. Visibility? No. No. View display. Bounds? No. In front? In front. Okay, there we go. See, that is the thing that wasn't being shown to me in all of the other videos. Okay. Viewport display in front. That is how you get that to work. Cool. Learning things. You can't learn like this nowadays. You have to find the ancient text.
When we rigged the ball with empties, we let the ball itself be the spin control for the rig. But when you rig with armatures, you want all of the rig controls to be inside the armature itself, so that all of the animation for the rig will go into one action. That means the ball can't be a rig control anymore. We are making the rig with an armature now, so the spin control needs to be a bone. Now go into edit mode on the armature, and position the bone to be the ball's spin control. And name the bone spin. Now go into pose mode and select the bone. You may notice that the rotation transforms on the bone actually has 4 components. That's because bones by default are set to use quaternions to represent their rotations. Quaternions have some important advantages when dealing with 3D rotations, and I'll explain them.
What the hell is a quaternion? What? Hold on. Quaternion. Before I look that up, I'm gonna do minus AI. I want define quaternion. Introduction to quaternions for aerospace application. Mathworks.com. What are you? Quaternions provide a compact, efficient, and numerically stable method for representing 3D rotations Unlike Euler angles, quaternions avoid gimbal lock and are more computationally efficient than rotation matrices. Oh boy. This efficiency makes quaternions ideal for aerospace applications such as spacecraft attitude control, aircraft orientation, and sensor fusion. Oh boy. No biggie. We're just going to use the fourth dimension to represent rotation. That's a new word. That's a new word to me. Quaternion. Oh boy. Ah. Okay. Okay.
What object to use by default. We can change the bone to use Euler rotations by clicking on this drop-down menu and selecting the XYZ Euler rotation mode. Now let's figure out which axis to spin on. Looks like it's the y-axis again, so lock the other two axes along with the rest of the transforms. Now we want to attach the ball to our spin bone. When you're in pose mode, you can still select objects outside of the armature as well. So select the ball, and shift select the bone, and hit Ctrl P to parent them. The menu that pops up is quite imposing. Remember when a menu popped up when we were just parenting objects, even though it only had one item? Well, this is why that menu exists. When you're parenting an object to a bone, there are many ways to do it. I'll just explain two of them for now. The first item on the list, object, means that you want to parent the ball to the armature object, not the bone. If we did that, then the ball would move if we moved the entire armature object, but not if we moved the bone. That's not what we want. The last item on the list, bone, is what we want. That will parent the ball to the bone we have selected. So, select bone from the menu. Now when we move the bone around, the ball moves too. Hooray! Next, let's create the counterspin bone. Go into edit mode on the armature again. Select the spin bone and hit Shift D to duplicate it. And let's move it to the side a little bit so that we don't get confused between the two bones. We'll move it back later. Let's name the bone MCH Counterspin. The MCH is for our own convenience as riggers, so we can tell at a glance that it's a mechanism bone, not a control bone. And
Cool. Cool.
the rest of the name describes what the bone is for. Let's drag the tip to make the bone a little smaller so we can distinguish it from the spin control bone when we move it back later on. And let's make it the parent of the spin control bone. Finally, let's create the main control bone for squash and stretch and location control. Position it at the center of the ball. Name it main. And make it the parent of the MCH counterspin bone. Now switch to pose mode again because we need to lock the bone's transform axes and add constraints. Add a maintain volume constraint to the main control bone. One of the nice things about bones is that their long axis, the one between their endpoints, is always the bone's local y-axis. So we know right off the bat which axis is the axis that we want to be free for the squash and stretch. However, if we go to the constraints panel, there aren't any constraints there. Hey, what's going on? We just added the constraints. That's because bones aren't objects. And this constraint panel is for object constraints. The constraints for bones are in a different panel here. Ah, there the constraint is. Awesome. Okay, now let's configure it. Oh, nice. Okay, well the y-axis is already the one that's set to be free. Well, we don't have to do anything then. But we do still need to lock the X and Z scale axes on the bone. Now if we scale the bone, squash and stretch! Yay. Okay, sweet. And now we just have to lock the rest of the axes we want on the main control bone, just like when we were using empties. is set up the counterspin driver. But before we do, let's take a look at what happens when we rotate the main control and the counterspin bone. Select the main control and rotate it to the right. Notice that it rotates on the z-axis in the negative direction. Now rotate the counterspin bone to the right as well. This bone rotates on the y-axis in the positive direction. How weird. What's going on? What's going on is that rotations on bones take place on their local axes, which are defined by their orientation in edit mode. So this means we want to drive the counterspin bone's Y rotation with the main control bone's Z rotation. It also means that the same rotation direction is positive on the counterspin bone and negative on the main control bone. So we don't have to make the driver negative like we did with the empties. It's already built into how the bones are oriented. So let's add the driver and start setting it up. I'll skim over this since we already did it once, but there is one thing I need to point out partway through. Okay, here's what I wanted to show you. With empties, we could just specify an object for the variable to reference. However, with bones, you have to specify both the armature that the bone is in, and then the name of the bone itself. And that's because different armatures can contain bones with the same names. So the name of the bone may not be unique. You have to tell Blender which armature the bone is in as well. So specify the armature object first, which we named rig, and then give it the name of the bone in the next field. We also need to tell the variable to use transform space. For now, just accept that we need to do that. The rest of the driver setup is exactly the same as before. Okay, cool. Well, now let's give this little rig a try. Oops, that's kind of a weird wobble there. What's going on? Well, what's going on is that we need to move the counterspin bone back into position. Remember, we offset it from the spin bone. Make sure you do it in edit mode, not in pose mode. And let's also move the counterspin bone to another layer. Remember that armatures have their own internal layer system, so we're moving it to another layer of the armature, not a layer of the scene. Select the bone, press M, and move it one layer down. Now it's hidden and out of our way. If you want to toggle the layer to be visible, go to the armature properties and find the skeleton panel. The armature layers are here. You can toggle them on and off by shift clicking, but I'm pretty happy with that mechanism bone being hidden, so I'm gonna leave it alone. We now have a functionally complete ball rig. Look at that. But there are still a couple of things that we can improve. The first is that we can move the main control down to the base of the ball. This is a good idea because the ball will often be squashing against something. Well, let me show you. Go into edit mode and move the main control bone down to the base of the ball. Remember that you don't have to worry about it dragging its children with it when you're in edit mode. Now when you scale it, it squashes against the ground. This reduces work for the animator, who would otherwise have to scale and move the control to accomplish this. The second thing we can do is make the controls prettier. The default bones appearance don't look all that nice, and moreover, they don't do a good job of communicating what the controls are for. One of the cool things about bones is that you can give them a completely custom look simply by telling them to imitate the look of another object. So for example, if we add a monkey head to the scene, we can make the main control bone look like it by selecting the bone in pose mode, going to the bone properties, and finding the custom shape field in the display panel. All we have to do then is click on the field and select the object we want the bone to imitate, in this case, monkey. Ta-da! The bone now looks like the monkey head. Notice though that it isn't in the same orientation as the monkey head. That's because the bone moves, rotates, and scales the shape of the object to match its own transforms, no matter what the transforms on the object are. This means that to change the appearance of the bone, you have to actually edit the mesh in edit mode. You can't just move the object around. Of course, a monkey head is not what we want our controls to look like. Fortunately, I have pre-made some shapes for us on the last scene layer. I've named the one for the main control WGT main, and the one for the spin control, WGT Spin. I use this naming convention so that it is easy to tell what bones the shapes are for, and so that I know they are for a distinct purpose compared to the other objects in the scene. Let's assign them to the bones. Select the main bone, go to the custom shape field, and set it to WGT main. Oops, the bone seems to have disappeared. But in fact it hasn't. What's going on is that the object we used for the custom shape only contains edges, not faces. For those edges to be visible, we have to set the armature to display wireframe. Go to the object properties, and in the display panel, change it from textured to wire. Yay, it's back. Now assign the shape for the spin bone. Awesome. You might notice that I built these shapes to be outside of the ball mesh. This is on purpose, because now we can turn off X-ray display. X-ray display can be quite confusing with more complex rigs, as controls overlap with each other. So I try to design my bone shapes so that it is not necessary to have X-ray display on. Finally, we have a completely finished rig. Good job. Now maybe we can move on to something other than bouncy balls. Our second rig is going to be a character that I like to call Mr. Squeegee Feet. I call him that because he has squeegees for feet. He's a great friend to have around when you want something squeegeed, and he's pretty much the only friend you ever want dancing on your car. Now, there are two different approaches we can take to rigging Mr. Squeegee Feet. The first is to dive right in and start rigging him. The second is to break him down into parts and figure out how to rig each of those parts one at a time. I'm going to take that second approach. I am not personally smart enough to tackle all the problems of a character rig all at once. It's easy to get confused and lose track of things. I prefer
Yay, small brain gang.
to take on one problem at a time, and then assemble all of the individual solutions in the final rig after I'm satisfied with them. I think this is usually the best way to approach rigging, and I strongly suggest that you do the same. So what parts of Mr. Squeegee Feet do we need to rig? Thankfully, he's a fairly simple character, so we really only need to rig a few parts. His eyes, his legs, his feet, and his body or head or whatever it is. That seems pretty manageable. We can figure out how to rig each of these parts separately, and then build the final rig using what we figured out. But before we do that, we need to figure out what Mr. Squeegee Feet is going to be used for. In fact, that's pretty much the first step with any rigging job, figuring out what the rig is going to be used for. It's just like designing anything else. If you're going to design an eating utensil, it's important to know if the person is going to be using it to eat soup or spaghetti. If they're going to be eating soup, they might need a spoon. If they're going to be eating spaghetti, they might need a fork. If you don't know what they're going to be eating, you could always design a spork, which will at least get the job done in either case. But if you know exactly what the utensil is going to be used for, then you can really design it to be amazing for that specific case. The same is true with rigs. Often you will know ahead of time what animations the rig is going to be used for, and you can then optimize the design of the rig for those animations, often resulting in a simpler, easier to use rig. Consider the bouncy ball from the previous chapter. For some situations, our first version of the rig, the super simple one, would have been fine. And if we knew those situations was all the rig was going to be used for, then we could have stopped there. On this DVD, I get to make up our requirements. And I will be specifying those requirements at the beginning of each chapter, so you can get used to thinking about rigging this way. Rigging is a means to an end, so you need to know what that end is. In the case of Mr. Squeegee Feet, I'm going to artificially say that we don't need squash and stretch. Mr. Squeegee Feet is sufficiently silly without that. I'm also going to say that the only things Mr. Squeegee Feet ever does is walk and look around. He doesn't fly or fall from great heights or do acrobatics or make facial expressions or anything like that. All he ever does is walk and look around. So, with those requirements in mind, let's get started. To kick things off, let's start with the legs. Get it? Kick things off. Legs.
Okay.
To make this leg rig effective, we need to think about what the most convenient way to animate a walk is, or at least what would be the least inconvenient way. To get the thinking started, let's find out what would happen if we rigged a leg as just a couple of bones that are the children of the body. Add an armature to the scene. Switch to side view and go into edit mode. Right now, we're just playing around. We're playing with ideas. The point of this is to just be free, with nothing considered sacred or final. This
Oh
is
yeah.
our playground for problem solving. Our problem-solving playground. So let's say that the default bone represents the body of the character. And let's add 2 more bones to represent a leg. Position them to be like the upper and lower parts of the leg. Now let's make the upper leg the child of the body. And let's make the lower leg the child of the upper leg. But in this case, instead of choosing keep offset, like we usually do, let's select connected and see what happens. How odd. The lower leg moved. Its top endpoint now lines up exactly with the upper leg's bottom endpoint. In fact, if we try to select this endpoint and move it, they both move together. The 2 endpoints are now merged into one. And this is what the connected item in the bone parenting menu means. When you connect bones together like this, they're called a bone chain. You can also quite easily create bone chains by selecting an endpoint and pressing the E key. This extrudes a new bone from that endpoint, which is a connected child of the bone you extruded from. To confirm, left-click. You can continue hitting E and left-clicking to extend the bone chain further and further. If we go into pose mode now, we can see that the translation transforms are grayed out. This is because you cannot translate bones that are connected to their parent. You can only rotate and scale them. But they do move, of course, if you rotate or move their parents. This connected feature is really just for our convenience as riggers, and it doesn't really enable anything special. We could manually line up the bones' endpoints and lock their location transforms to get pretty much the same effect. But there are a lot of cases where you want these sorts of chains of bones, and this connected child feature, it just makes it a lot easier for us to manage. Let's go back into edit mode and delete all the bones except the body and leg bones. Now to test this simple leg rig that we've just created, let's go back into pose mode. and if you think this is a lot of mode switching, you have no idea what you're getting into. There will be so much more mode switching as we get into more complex rigging.
Yep.
Let's say that we're going to animate a walk with this. Never mind that there's only one leg. Pretend there's another one. Use your imagination.
I might need more tea.
Between all walks is that at some point in time, a foot is going to be on the ground, and it will remain relatively stationary while it's there. It's also a common similarity that during this time, the body is going to continue moving forward, because, walking makes you move forward. So the question now is this easy to accomplish with this rig? Let's try. Mark where the foot is supposed to be with an empty. Now move the body forward. Okay, well, now we need to adjust the leg to keep the foot in place. Okay, now move the body forward again. And now we need to adjust the foot again. Well, this is kind of tedious. Plus, what if we were actually animating this, and we decided we wanted to subtly adjust how the body was moving forward? Then we would have to redo all of the leg positions again. That sucks. So hopefully you can see that this is a pretty terrible solution for a walking leg rig. What we really want is a way for us to be able to make the foot stay put and make the body move forward, all while the leg automatically stays properly attached to both. As it turns out, there is a great way to do this, and it's called inverse kinematics. Inverse kinematics in its simplest form is a way to instruct a bone chain to try really hard to keep its tip connected to something else without moving its base. Sometimes this is impossible, for example, if that something else is too far away or too close, but it tries really hard. In this case, we can use inverse kinematics to tell our leg to stay connected to the foot whenever possible. To do this though, we first need a foot bone. So let's add another bone near the end of the leg to represent the foot. We also need to make sure that the knee is slightly bent in edit mode, so do that if you haven't already. I'll explain why that's important in a later section of the DVD, but in a nutshell, it's going to tell the inverse kinematics solver which direction the knee should bend. Now we need to add the inverse kinematics. In Blender, inverse kinematics is considered a constraint, although it actually operates outside of the constraint system to an extent, but I'll explain that later when I discuss how the constraint stack functions. But for now, let's keep it simple. Inverse kinematics is the first constraint we're going to use that involves one bone affecting another bone. Remember that there are two ways to add constraints: via the constraints panel or bone constraints panel, and via a hotkey in the 3D view. To add the inverse kinematics constraint via the bone constraints panel, we need to select the last bone in the chain, because even though the constraint will affect both bones, IK constraints always exist on the last bone we want affected in the chain. Now add the constraint via the menu.
Okay. Inverse kinematics.
Requires a target for the bone chain to attempt to stay connected to. If we don't specify one, the IK constraint has no goal, and it won't really do anything. In this case, we want it to stay connected to the foot, so the foot is our target. Click on the target field in the IK constraint. Just like with driver variables, we first have to specify the armature object, and then the bone name. So specify the armature in the first field. Now we can specify the bone in the bone field. Oh my. Which of these is a foot bone? They're all just named bone, with a number pendant on the end.
Yeah, I should have named your bones.
So let's do that before we move on. Okay, much better. This is one of the reasons it's important to name things in our rigs. It makes things less confusing, not only for other people that look at the rig later, but it also makes things a lot less confusing for us. Okay, now let's specify the foot in the bone field. Wow! It just immediately snapped to connect with the foot bone. But before we move on, let's see how to add this using a hotkey. To add a constraint where one bone affects another, you first select the bone that will do the affecting, and then you select the bone that will be affected. This is kind of the reverse of specifying parents, which can make this confusing and hard to remember. Unfortunately, we just need to put up with that. Next, hit Ctrl-Shift-C and select Inverse Kinematics. Ta-da! Now we have an IK constraint with all the target information filled out for us. This is a much faster way to add constraints, and it's the way that I usually do it. Now let's try moving the foot bone around. Nifty.
Nice.
The leg stays connected to it. However, notice that the body bone is moving too. How strange. It's not part of the leg's bone chain. The reason this happens is because inverse kinematics actually isn't limited to just bone chains. It actually functions on any parent-child hierarchy of bones. It will keep searching up the hierarchy, parent to grandparent to great-grandparent, until it can't find any more bones. To limit the constraint to the leg bones, we need to specify a limit on how far up the hierarchy it searches. And thankfully, this is extremely simple to do. We just change the chain length. 0, the default value, is a magic number for this field, and it means unlimited. But any other number, such as, for example, 2, tells it that we only want it to affect, in that case, 2 bones up the chain. And since we only have 2 leg bones, that is indeed the number that we want. Now when we move the foot, only the leg bones move. Yay!
Wonderful.
So if we move the body, the leg sticks too. Woohoo!
Oh yeah.
So IK, or inverse kinematics, seems pretty magical, and in a lot of ways it is. But we're still going to run into some problems with it if we just leave it how it is right now, and that's because inverse kinematics is an under-constrained problem. What on earth do I mean by that? Well, to start with, I'm not talking about Blender's constraint system. I'm using the word constrained in a different sense now. In this case, when I say that inverse kinematics is solving an under-constrained problem, I mean that there are multiple possible solutions. If we have a two-bone chain and a point that we want it to reach, there are actually multiple solutions. It could bend this way, or it could bend that way. And in 3D space, the bones can twist and rotate around every which way. In fact, there's an infinite number of solutions to this problem. And it only gets worse if we have more than two bones. Then even when restricted in 2D space, there's still an infinite number of solutions. That's what I mean when I say that IK is an under-constrained problem. The IK solver has a lot of wiggle room to choose its solution from. Now, in a lot of cases, this simply doesn't matter. Blender's IK solver does a pretty good job of finding smooth, sensible solutions to the problem. But in this case, we really do care about the specific solution. In particular, knees-on bipedal creatures only bend on one axis, and Mr. Squeegee Feet is no different. Unfortunately, the IK solver doesn't care about that, and it will bend the shin bone in any direction it likes. Fortunately,
Erroneous.
the IK solver to care. Select the shin bone, and go to the bone properties. Find the inverse kinematics panel, and toggle it open if necessary. There are a bunch of parameters in here, all of which allow us to configure how the IK solver uses this bone. In this case, what we care about are these toggles with the lock icons. These allow us to tell the IK solver not to rotate on these axes. It's just like locking rotation axes for manual rotation in the 3D view, except this is for the inverse kinematics solver. We want the knee to only bend on one axis. But which axis? Let's go find out. We can't very easily rotate the shin bone right now because its rotation is controlled by the IK constraints, but I have a new trick to show you that will let us figure out the bone's axes without rotating anything. Go to the armature properties and find the display panel. There's a checkbox labeled Axes. Click it. Aha! Suddenly, there are weird arrows sticking out of our bones with letters attached. Let's take a closer look. These are visualizations of the bone's axes. For rotations, the bone will rotate around the axes, so we can see then that the axis we want the knee to bend on is the x-axis. Return to the bone's IK properties and lock the other two axes. Now when we move the foot, the knee only bends on the x-axis. Woohoo! Because of the length of my explanations, this may already seem really complex, but let's take a look at what we've actually done so far. We've added a two-bone chain for the leg, we've added an IK constraint to make the leg stick to the foot, we've told the IK to only affect the leg bones, and we've told the IK solver to only bend the knee on one axis. So we really haven't actually done that much yet, and it's not really so complex. I'm just long-winded. Sorry. But we do still have one last step before this is a finished leg rig, and that is to give the animator control over what direction the knee is pointing. Right now, the knee direction is pretty much up to the IK solver. It will generally point in the right direction, for reasons that I'll explain when we look at IK more in depth. But there are still situations where the animator will need direct control, for example if they are animating an old man with wobbly knees. There are a couple of ways to do this, but my favorite for bipedal characters is called a pull target. To explain how a pull target works, imagine that we drew a straight line between the base of an IK bone chain and that chain's target. If we rotate the entire bone chain around that line, as if the line were an axis, the bone chain would still reach the target exactly, no matter how we spun it around that line. What a pull target does is it limits that part of the solution. It's a secondary target that tells the IK bone chain how to orient itself around that line. Let's dive in and try it out. Go into edit mode and add another bone in front of the leg. Name it pull target. Now go to the leg's IK constraint and specify that bone as the pull target. Remember that just like everywhere else that you specify a bone, you need to specify the armature first. you'll notice that immediately the leg rotates to kind of an odd angle. This is because the pole target is forcing it to spin into that position. If we switch to a top view and move the pole target around, we can see that the leg spins around exactly as much as we move the pole target around it. The basic idea is that if you imagine a line connecting the leg to the pole target, the angle of that line determines the spin of the leg. Of course, having the knee point off to the side of the pole target isn't very intuitive for animators. It would be much better if the knee pointed at the target. Fortunately, this is easy to adjust. Go to the IK constraint again, and find the field labeled pole angle. We can adjust the offset from the pole target here. Much better. Now the knee points at the pole target. Something important to notice about the pole target is that if we switch to the side view again and move it up and down, it doesn't do anything. This is because the only thing that matters about the pole target is its position around the line, not the position along it. I find the easiest way to think about this is to look straight down the line between the base of the bone chain and the IK target. Only the motion of the pole target on this view plane matters. Now, if we move the foot, that line moves. And the plane of motion that matters moves too. We can move the pole target huge distances along that line, and it doesn't affect anything. Only the position around the line matters. Now, one last thing to do is make the pole target the child of the foot. That may seem kind of weird, but it makes things a little bit more convenient, since feet and knees usually point in roughly the same direction along the IK line. This way the animator can better ignore the pole targets when they don't need to do anything special. Now that we have the pole target set up, we're finished designing the leg rig. Hooray! We can move the foot, and we can move the body, and control where the knee is pointing. This leg rig design is called an IK leg, because it is designed entirely around inverse kinematics. By contrast, our first attempt at a leg rig, where we manually rotated the leg joints, is called an FK, or forward kinematics leg rig. Put simply, forward kinematics is when you rotate a bone chain joint by joint, whereas an inverse kinematics rig is a rig like the one we just created, where the rotations of the bones are automatically calculated based on a desired target. Both kinds of rigs are useful for different situations, and later on we'll learn how to build a rig that lets us do both. But for now, we're going to leave it as is, because we know we're only going to use this rig for walking, so we don't need FK. Next up is feet, and thankfully, we're going to keep Mr. Squeegee's feet very simple. The model just has two pieces per foot, the heel and the toe. And we're going to take the easy way out for this rig and just have one bone for each.
Yep.
But even so, there are some things that we need to think about. The first is translation and rotation axes. The translation and rotation axes of bones are determined by the bone's orientation in edit mode. I touched on this briefly before, but I'm going to go a bit more in-depth into it now. Let's take a look at this armature I've prepared for us. We can see the rest position of the bones by entering edit mode on the armature. I've enabled axis display so that we can see the axes of the bones, and we can see that the y-axis of this bone is pointing off at an angle. Now, if we go into pose mode and play with this bone's y translation, we see that the bone moves along that local axis of the bone. Even if we rotate the bone in pose mode, that original edit mode orientation is still what determines the translation axes. Moreover, if we give the y translation a value of, say, 3, and then change the bone's orientation in edit mode, then in pose mode, its position changes. This is because the y translation value is now operating on the new y-axis, and is going in this direction instead of this direction like it was before. This applies for all of the translation axes, not just the y translation axis. And it also applies to the rotation axes. If we switch the bone to Euler rotation, and play with its y rotation axis, we see that it rotates around the bone's edit mode y-axis as well. These oriented axes, with their custom zeroed out positions, are called the local space of the bone. You may have noticed me using that term before, and it is in contrast to something called world space, or sometimes also called global space. World space is the overall space of the scene that everything exists in. If we have a bone floating in the scene somewhere, its world space translation might be something like x equals 2 and y equals 3.
Okay.
It's the absolute translation coordinates of the bone in the scene. On the other hand, if its rest position in edit mode was off here somewhere, oriented at an angle, then the local space translation of the bone might be x equals 2, y equals 1. One way to think of this is to say that the world space is the absolute coordinates of a bone in the scene, whereas local space is the relative coordinates of a bone compared to its resting pose. But bones are not the only things that can have local spaces. They're just the only thing whose local space we can set directly. By default, an object's local space corresponds exactly to world space. But that can be changed if, for example, you give it a parent. In fact, we exploited that in the bouncy ball rig. Remember that when the parent was rotated, the translation axes of the ball changed with it. We were indirectly changing the local space of the ball via a parent. And that happens with bones as well. If we rotate the parent of this bone, then its local space rotates too. So the local space of both objects and bones is affected by their parents, but only the local space of bones can be directly set by us. Whew, that might be a lot to take in, and I apologize if that's the case.
Yeah, it is a lot to take in. I am utterly confused. I thought you were going to rig a foot.
Spaces are an important concept in computer graphics and rigging, but they can also be kind of mind-bending. So for now, I'll just leave it at this, and we'll revisit later. But one last thing. It is important to realize that the coordinates we see here in the end panel, and that the animator will be animating with, always represent the local space transforms of the object or bone. In other words, animators are always animating in local space. And that's why we care about this with the foot. We want to place the foot bones so that their local translation and rotation axes make sense for the animator. If we put the foot bone at an angle, then there wouldn't be a simple single axis for up and down. Also, there wouldn't be a simple single axis for pivoting the foot around its heel. But it's helpful for the animator to have those simple, well-aligned axes, because it makes it simpler for them to, for example, tweak just the height of the foot, or manage the interpolation of the height of the foot. And these are important things for the animator to be able to do. So for our foot rig, we need two bones, the main foot bone and the toe. And the toe will be the child of the foot. And since we want them to have their axes nicely aligned, let's make them horizontally straight. To keep things simple, we're going to assume that the foot bone will be the direct target of the IK leg. So that means that it will need to be positioned where the leg is going to connect to it, which is at the ankle. And that's just a bit higher than the toe. We also want to consider which axis is the up axis for the foot. In Blender, the Z-axis is considered the de facto up axis, since that's what world space uses. Let's turn on axis visualization so that we can see if that's what we have or not. Uh-oh. Looks like we have some adjustments to make. Fortunately, Blender lets us roll bones in edit mode. Select the bone, and press Ctrl-R to roll the bone in edit mode. You can also change a bone's roll in the end panel here. By positioning the endpoints of bones and setting the roll, you have complete, full freedom to place the bones however you want. Now in pose mode, we also want to consider axis locking and rotation modes. Since the toe is just the floppy end of a squeegee, we really only need it to rotate on one axis. That means that we should first switch it to Euler, and lock all of its axes except the x-axis, which is what we want it to rotate on. Toes are also typically attached to their foot, so let's lock the toes' translation axes too so that it doesn't separate from the foot. Now Now, the foot itself, we can pretty much leave alone. It needs to be able to translate, so no locking there, and it is potentially going to be rotating on all rotation axes, so quaternions make sense for it. And there we go, a super duper stupidly simple foot rig. And yes, somehow I still managed to fit in a confusing topic. Woohoo! Eyes, the window into the soul, or lack thereof. I'm not really sure that Mr. Squeegee Feet has a soul, after all the squeegees for feet. But still, he needs eyes to see. Unlike the leg and foot rigs, for this rig, I have actually imported the eye meshes into our little rigging playground. We could have done that with the legs and feet too, and I encourage you to do that if you want to when testing out rig ideas. I've done it with the eyes because I think it will make the rigging a little less confusing when we get to our final solution. To start off, we clearly need to have at least one bone each for the eyes to be the children of, so let's add those. And let's rotate both of the eye bones down so that their y-axes are pointing in the same direction as the eyes. And let's position them at the center of each eyeball. To do this exactly, we can use Blender's cursor snapping tools. Select the eye, go into edit mode, and Alt-right click on one of the center edges to select an edge loop. Press Shift-S and select Cursor to Selected from the menu. This snaps the 3D cursor to the average position of the selection, which in this case will be the center of the eye. We could also do this in object mode with just the object selected, but that won't work if, for example, the eyes are part of a larger mesh. Now go back into edit mode on the armature. Select the eye bone, hit Shift-S, and select Selection to Cursor. Now the eye bone is positioned exactly at the center of the eye. Now do the same for the other eye. And let's name the eye bones I.L and I.R for the left and right eyes. And finally, let's parent the eyes to the bones. Remember, you need to be in pose mode to do this. Now, if we wanted to, we could just stop here. These two bones could serve as controls for the animator, but I think we can do better. For one thing, a pair of eyes generally both do the same thing. If one eye looks left, the other usually looks left as well. This is because our eyes are wired to both look at the same point in space. But unfortunately, right now our poor little animator would have to manually manage both eyes. So one way that we could improve this rig would be to directly emulate the tracking behavior of eyes by having a target that the eye bones track. In fact, that's a really common and useful way to set up eye controls on characters, so let's do that. Add another bone smack dab in front of the eyes. Let's name it Eye Target. To make the eye bones track this target, we're going to use constraints. Select the target, and then one of the eye bones, and press Ctrl-Shift-C to bring up the constraints menu.
Alt-Shift-C?
Section of the menu, we have a lot of constraints, but there are only two that really do what we want. Damped Track and Track 2. Both of them behave similarly in that they both will make the bone rotate to track a target, but Damped Track does it in a smoother, more stable way. There are situations where Track 2 may be what you want, but for most situations, Damped Track is a better choice, so choose Damped Track. You'll notice that the eye bone immediately snaps to point at the target, and the eye mesh goes along with it. And if we move the target, the eye tracks it. Woohoo! Let's do the same for the other eye. Yay! Now they're both tracking. But this still isn't entirely ideal. For one thing, the eyes have snapped to a slightly cross-eyed position. This is realistic, of course, since they are looking at a point relatively close by, but it may not be how we want our character to look. With this rig setup, we would have to move the target really far away for the eyes to appear like they did before. But that's kind of a nightmare for the animator to manage, since they'll have to zoom way far out every time they want to adjust the eyes. So what if instead we find a way to keep the eyes uncrossed no matter how close the eye target is? One obvious way to do this is to create two eye targets that are eye distance apart, and make them children of a master eye target control. Let's give that a try and see what happens. Add two more bones to be the child eye targets, and position them eye distance apart. Make them the children of the eye target. Now remove the existing constraints from the eye bones, and replace them with a damped track to their respective targets. Yay! Now there is no more cross-eyedness, and we can move the target as close as we want, and no cross-eyedness happens. But there is a problem. What if the head were to turn? We don't have a head bone, but we can still simulate this by selecting the eye bones and rotating them. Yeah, that's terrible. The eyes have gone all weird and cross-eyed again. And this is because the positions of the secondary eye targets are no longer aligned with the eyes. The animator would need to rotate the eye target to stay aligned with the eyes at all times. And guess what? That sucks. It's bad. It's unnecessary work for the animator. They shouldn't have to worry about that. So scrap that. It was a decent idea, but in practice, it turns out it's got problems. And a lot of rigging ideas are like that, actually. Most of my ideas never make it into final rigs, because I find problems with them in the playground phase.
Yep.
It's normal, and that's fine. The important thing is that you don't get so married to an idea that you ignore other solutions that might be better. So let's look for a better solution. What, fundamentally, do we want these eye bones to do? What limitation are we trying to impose on them? Well, we want them to stay parallel to each other. Or in other words, we want them to have the same rotation. Well, heck, there's an easy way to enforce that. A copy rotation constraint. They can't have different rotations if one of them is forced to copy the rotation of the other. So one way we could do this is to have one of the eyes track the target, and have the other eye copy the rotation of the first. But we'll run into problems with that too, because then both eyes will look off to the side when the eye target gets close. So what if instead we had both eyes copy the rotation of a third bone that tracks the target? Then we could place that third bone in the middle, so that it doesn't shift strangely when the eye target gets near. Yeah, that sounds like a good idea. Let's do it. Clear out the stuff we just did by deleting the extra eye targets and clearing out the constraints. Now duplicate one of the eye bones and move it smack in the middle of the eyes. Name it Mind's Eye. Mind's Eye. Now add the copy rotation constraint to the eye bones, making them copy the rotation of the Mind's Eye bone. Now when we rotate the Mind's Eye bone, the other two rotate with it. Cool. Now we just have to make the Mind's Eye bone track the eye target, and voila! Moving the eye target around now makes the eyes track it. But they stay parallel to each other instead of being cross-eyed. Nifty. There's still one last thing that we could do though, and that is to let the animator also animate the eyes individually on top of all of this. Do you remember how to do that? If something is automated, but we still want the animator to be able to animate on top of that automation,
Right.
what do? We add parents, and automate the parents instead. So let's duplicate the eye bones to create some parents, and let's scale them down a bit so we can tell the difference between them and the eye bones. Now let's make the eye bones the children of those. And let's remove the eye bones constraints. And thankfully, when you duplicate bones, they take their constraints with them, so the parents already have the copy rotation constraints on them, but if they didn't, then we would add those at this point. So now we can move the eye target around, and we can also rotate the eyes manually if, for example, we wanted to make the character cross-eyed. Lastly, let's lock the translation axes on the eye bones, just so that the animator doesn't accidentally pull the eyes out of their sockets. And let's align the eye target so that Z-axis is up. And that's it. We now have a pretty decent eye rig setup.
Wonderful.
We now have the legs, the feet, is? Well, in the case of Mr. Squeegee Feet, his body head thing is really just a big ball, and it really only needs one bone. We want to make sure to orient that bone well so that the local space for it makes sense for the animator, but other than that, there's not much to do. So let's just move right along to putting it all together. First, let's add an armature and put it into X-ray and wireframe display, and turn on axis visualization. Let's make this first bone the body bone. Move the bone a bit below the center of the body sphere, so it will rotate a bit more like hips during a walk. And align it so that the z-axis is pointing up. This way, the up-down translation axis will be the z-axis, just like everything else. Name the bone Body. And now let's add the thigh bones for each leg. Name them thigh.l and thigh.r. Now this L and R naming convention for left and right versions of the same bone is not just for clarity, although it is for that too. But if we name our bones this way, we can take advantage of a cool feature in Blender that automatically keeps bones mirrored across the x-axis of the armature. In the T panel, the panel on the left of the 3D view, there's a checkbox that appears when we're in armature edit mode, labeled x-axis mirror. Turn it on. Now, if we move one of the leg bones, the other stays the exact mirror of it. And this is going to help us set up the armature a lot.
Okay. So, armature edit mode. T. X-axis mirror. Okay, maybe I just don't know enough. Maybe I just don't know enough. Armature tools. X-axis mirror. Duplicate and rename. Somebody's blasting music. Duplicate, rename, rename. Yeah, I don't think that music is going to end up stopping, so I guess I'm gonna have to stop streaming. That's that's annoying, and I hate that I get triggered by the noises. So I'm gonna have to end the stream here. Yeah, exactly. I'm in hell. So, like and subscribe. Bye bye.